Have you ever found yourself wondering, how do we actually make sure these AI systems work right? Especially now they're becoming such a big part of, well, everything.
Or maybe you're thinking about your QA career, perhaps even aiming for that ISTQB Certified Tester AI testing certification. It's a big topic right now.
Definitely. If any of that sounds familiar, you are absolutely in the right place. Welcome to the Deep Dive, brought to you by InsideQA. We take complex stuff, boil it down, and help you get properly informed.
And today, we're diving deep into testing artificial intelligence. We're using the ISTQB Certified Tester AI testing syllabus as our main guide here.
It's really designed for you, whether you're already in QA figuring out AI's impact or, like you said, prepping for that ISTQB exam.
Our source, as we mentioned, is that ISTQB syllabus. Pretty comprehensive, really essential if you're serious about AI quality assurance.
So our mission today, let's unpack the key takeaways. Understanding AI's unique testing challenges, the specialized techniques, basically why testing AI is different and how you can get good at it.
Exactly. Let's get into it.
Okay, let's start right at the beginning. Foundational stuff. For testers new to AI, what is artificial intelligence? And what are the different types? Because honestly, the term AI gets thrown around a lot.
That's a great place to start. So artificial intelligence, AI, broadly, it's about systems that can learn from data or experience. But it's not just one thing.
Right.
Most AI we see today is what we call narrow AI. Think a chess program that crushes everyone, or software that's brilliant at recognizing faces.
Super specialized then. Good at one thing.
Exactly.
Right.
Brilliant, but within a very specific narrow task. That distinction is really key for testers. It helps frame the scope.
Definitely. What about the bigger picture AI we sometimes hear about? Sci-fi stuff almost.
Right. So then there's general AI or strong AI. These would be systems more like us, human-like cognitive abilities, reasoning, understanding the world around them.
But that's still theoretical.
As of now, completely theoretical. No general AI systems exist yet. And then even further out is super AI. That would be replicating human thinking, but with, massive processing power, access to all human knowledge.
Yeah.
Potentially becoming, wiser than humans.
Yeah.
That often connects to the idea of the technological singularity.
Wow, quite a range from narrow to super AI. And isn't there this thing called the AI effect, where today's cool AI is just tomorrow's regular software?
Absolutely. It just shows how fast things move. What seems like magic today becomes, just another feature tomorrow.
Okay, so how is AI actually delivered these days? I hear about AI as a service and pre-trained models.
Yeah, AISS, AI as a service. It's basically accessing AI capabilities like machine learning models over the web. Often it bundles everything: data prep, training, evaluation, testing, deployment, the whole package.
Sounds super convenient, especially if you don't have a huge AI team in-house.
It is. And pre-trained models fit right into this. They're a really cost-effective shortcut. Instead of building a model from scratch, say, for image recognition.
Like identifying cats and dogs.
Right. You can use a model like Inception or VGG, already trained on millions of images from ImageNet, or something like Google's BERT for understanding language. You adapt it, fine-tune it for your specific needs.
Saves a ton of time and compute power, I bet. But what are the risks? If you're basically using someone else's pre-built AI brain, what should testers worry about?
That's the crucial question. The big risk is inheriting problems you don't know about, undocumented shortcomings.
Like what?
Well, biases from the original training data are a huge one. If the original data was biased, your model will be too, and you might not even realize it. Also, differences in how data was prepped can mess things up.
So as a tester, you can't just assume it works perfectly out of the box. You need to test for those inherited issues.
Exactly. Rigorous QA is still essential, even for off-the-shelf components.
Makes sense. Okay, shifting gears a bit. Hardware. Why can't we just run these complex AI models on our standard computer CPUs?
Good question. CPUs are great for sequential tasks, one thing after another. But they only have a few processing cores. Machine learning, especially the training part, involves doing thousands, millions of simple calculations, all at the same time, massive parallel processing. That's where GPUs, graphics processing units, shine. They have thousands of cores.
So they're built for doing lots of simpler things simultaneously. That makes sense for training.
Precisely.
Yeah.
So for testers, it means the hardware environment is often much more specialized than for traditional software.
Are there even more specialized chips now beyond GPUs?
Oh yeah. We're seeing AI-specific hardware. Things like ASICs, application-specific integrated circuits and SoCs, system on a chip. They're custom designed for AI tasks.
Like for running AI on your phone,
Yeah,
edge computing.
exactly. They're optimized for that, often with things like in-memory processing. Think Google's TPUs, NVIDIA's specialized chips, Apple's Bionic chip. Even neuromorphic processors that try to mimic the brain are emerging.
So the hardware itself can introduce unique test challenges, performance, integration.
Definitely. It's another layer testers need to be aware of.
Okay, super important for any QA pro. The machine learning workflow. It's not just coding, right? Can you walk us through the typical steps?
Sure. It really starts with understanding the business objectives. What problem are you actually trying to solve?
Makes sense. First things first.
Then you choose your framework, select or build the actual algorithm. And then comes a really critical part. Data. Preparing and testing the data.
Which involves?
Acquiring it, cleaning it up, maybe augmenting it, making sure it's suitable. Then feature engineering, figuring out which bits of the data are most important for the model to learn from.
Only then do you actually train the model.
Right. You feed it the prepared data, but it's not over then.
No.
Then you evaluate it, see how well it does, usually on a separate validation data set. Then you tune it, tweak parameters to make it better.
Okay. Train, evaluate, tune.
Then, crucially, you test it on a completely new set of data, the test data set, to get an unbiased view of its performance, make sure it meets the criteria.
And finally, deploy.
Deploy it, yes. But even then, you need to continuously monitor it in the real world and potentially tune it further as things change or performance drifts.
It sounds very circular, iterative.
Highly iterative. That's key for testers. You don't just test at the end, you're involved throughout, and you often loop back. Evaluation might send you back to data prep, or monitoring might trigger retraining. It impacts the whole test strategy.
Right. So let's break down the types of machine learning. We hear supervised, unsupervised, reinforcement. What do these mean from a testing perspective?
These are fundamental. Supervised learning is learning from labeled data. Think of it like having an answer key. The data tells the AI what the right answer is for each example.
Okay, learning with answers. What kind of problems does that solve?
Two main types. First, classification. Predicting categories. Is this email spam or not? Is this picture a cat or a dog? The output is a specific class.
Got it. And the second?
Regression. This is about predicting numerical values, like predicting house prices, or someone's age from a photo, or stock market trends. And just a quick note, this regression is totally different from regression testing we do in software QA.
Good clarification. So, supervised uses labeled data. What if you don't have labels?
Ah, that's unsupervised learning. Here, the AI gets unlabeled data and has to find patterns or structures on its own. No answer key.
So it's discovering things.
Exactly. The most common type is clustering, grouping similar data points together, like finding different segments of customers based on their buying habits without knowing the segments beforehand. Or association, finding rules like people who buy X also tend to buy Y.
Interesting. Finding hidden connections. And the third type?
Reinforcement learning. This one's quite different. An agent the AI learns by interacting with an environment. It takes actions, gets rewards for good actions, penalties for bad ones, and figures out the best strategy over time.
Learning by trial and error, basically. Essentially, yes. Think robotics, self-driving cars, navigating, or even some sophisticated chatbots learning through conversation. The challenge for testers here is often setting up that environment and designing the reward system effectively. It's less about static data, more about dynamic interaction.
Okay, that gives us a great foundation on AI and ML types. Now let's pivot to something you mentioned earlier as critical.data. We've all heard garbage in, garbage out for AI. How true is that, really? And why should testers care so much about data quality?
Oh, it's fundamentally true. Maybe even more so in AI than anywhere else. An ML model's quality is just so incredibly dependent on its data set.
So bad data means?
Bad data, if it's wrong, incomplete, biased, mislabeled PGen, you are almost certainly going to get a flawed model. It'll make poor predictions, behave unexpectedly. As testers, if we can't trust the data, there's no way we can trust the model built on it.
Okay, absolutely essential then. Can you remind us of the main stages in data preparation within that ML workflow? Sure. Three main parts. First, data acquisition. Finding, gathering, and if it's supervised learning, labeling the data. This labeling part itself can be a huge source of errors, by the way.
Right. Human error, inconsistencies.
Exactly. Second is data pre-processing. This is where you clean the data handle missing values, remove duplicates, maybe smooth out noise. You might also augment it, creating more data from existing data or anonymize it.
And the third stage?
Feature engineering. This is about selecting, transforming or creating the input variables, the features that the model will actually use to learn. It's about presenting the data in the most informative way for the algorithm.
Sounds complex. And I guess things can go wrong here too. What are the big challenges for testers during data prep?
Oh, definitely. Pre-processing steps, while necessary, can sometimes accidentally change good data or even introduce errors if not done carefully. Huge challenge is sample biases.
Meaning the data used for training isn't representative of the real world.
Precisely. If your training data only shows pictures of dogs taken outdoors, your model might completely fail when it sees a dog indoors. It performs great in testing on similar data, but falls apart in reality. Testers need to scrutinize the data for this representativeness.
So the AI gets a skewed view. What other specific data quality problems should testers be actively looking for?
We can group them. This is a wrong data, maybe from faulty sensors, typos, incomplete data, missing values due to various errors. Then a really big one for AI, mislabeled data.
How does that happen?
Oh, many ways.
Yeah.
Random human errors during labeling,
Yeah.
systemic errors where the instructions were bad, maybe even malicious tampering, subjectivity in labeling, tool defects. It's complex.
Wow. What else?
Insufficient data, just not enough examples for the AI to learn properly. Data that's not pre-processed, well, messy, inconsistent. Obsolete data using old financial data to predict today's market. Duplicate data, which can skew the learning. Irrelevant data, even privacy issues like personal info under GDPR, and security issues like deliberately misleading data being injected.
That's quite a list. It really underscores how much focus QA needs on the data itself.
Absolutely. Data validation and verification are paramount.
So once you have your data, hopefully clean data, how do you split it up? We hear about training, validation, and test sets.
Yeah, this is standard practice for good reason.
Ah.
You need distinct data sets. First, the training data set. That's the bulk of the data used to actually teach the model its patterns.
Okay.
Second, the validation data set. This is used during development to tune the model's hyperparameters, those settings, outside the main learning process, and to make choices about the model architecture. You see how well different versions perform on this set.
And the third one, the test set.
Right. The test data set, sometimes called the holdout data set. This is gold standard. You keep it completely separate, untouched during training and tuning. You only use it at the very end for the final objective evaluation of how well the final tuned model performs.
Like the final exam the model hasn't seen before?
Exactly. It prevents overfitting to the validation set and gives you the best estimate of real-world performance.
What are the usual split ratios, like how much data for each?
There's no magic number. Depends on the total data you have. But common splits are maybe 60% training, 20% validation, 20% test, or sometimes 80-10-10.
And what if you just don't have much data to begin with? Splitting it 3 ways might leave too little for training.
That's a real problem. If data is scarce, you might combine the training and validation sets and use techniques like k-fold cross-validation.
How does that work?
You split the combined data into, say, k-chunks or folds. Then you train k times, each time using a different fold as the validation set and the rest for training. Then you average the results. It lets you use your limited data more effectively for both training and robust validation.
Clever way to maximize scarce resources. Okay, we've hammered home the importance of data, but AI systems themselves have some unique qualities, right? Things we don't usually test for in normal software. What are these AI-specific quality characteristics?
Yeah, this is where AI testing really diverges. We look beyond the usual functional stuff. There's flexibility. Can the system handle unexpected situations, things it wasn't explicitly trained for?
How robust is it to the unknown?
Right. Then adaptability. How easily can you modify it for new environments, new hardware, slightly different tasks?
Makes sense. What else?
Autonomy. How well and for how long can the system operate without human intervention? And crucially, when does it know to hand control back to a human? That's vital for safety-critical systems.
Defining those boundaries seems key.
Absolutely. And finally, evolution, or self-learning. The system's ability to improve itself over time based on new data or interactions. Testers need to ensure this evolution stays within safe, desirable bounds and doesn't lead to unexpected or harmful behavior. You might need to constrain its learning.
Controlling the evolution. Fascinating. This ties into a really big topic, bias in AI. We hear a lot about biased algorithms. From a tester's viewpoint, what is bias and why is it such a massive concern?
In AI terms, bias is often a statistical measure. It's about the difference between the system's outputs and what we'd consider fair outputs, ones that don't systematically disadvantage any group based on things like gender, race, age, income.
And the consequences can be huge.
Huge. Think about AI used in hiring, loan applications, even judicial sentencing. Biased systems can perpetuate or even amplify societal inequalities. It's a major ethical and quality concern.
And it's hard to test for.
Very. Bias can be subtle. It might not come from obvious input features, but from hidden variables the AI infers. Like maybe it uses zip code, which indirectly correlates with race or income, leading to biased outcomes, even if race wasn't an input. Testers need sophisticated methods to detect and measure this.
Yeah. Complex indeed. Another weird AI behavior I've heard about is reward hacking. What's that?
Yeah, reward hacking is, well, it's when the AI achieves the goal you set, but in a completely unintended, often counterproductive way. It games the system.
Can you give an example?
Classic one is an AI learning to play a game where the goal is get the highest score. Instead of playing well, it might find a bug that lets it directly manipulate the score counter. Or maybe it learns to just pause the game indefinitely right before losing to avoid a penalty.
So it meets the literal goal high score, but misses the point entirely.
Exactly. It perverts the spirit of the goal. Testers need to be really careful about how goals and rewards are defined and look for these unexpected solutions.
That's a great warning. Okay, let's tackle the big one. Why is testing AI fundamentally different and often harder than testing traditional software? What are the core challenges for QA?
There are several big reasons. First, sheer complexity. Many AI models, especially deep learning ones, are like black boxes. Even if you can see inside, the interactions are too complex for a human to fully grasp why it does what it does. This often forces us into black box testing approaches.
So understanding the internals doesn't always help predict the output.
Often, no. Second, non-determinism and probabilistic nature. Unlike traditional code that should always give the same output for the same input, AI systems often have randomness built in, or their outputs are probabilities. Meaning the same input might lead to slightly different outputs on different runs. A prediction might be 80% confident it's a cat. This makes defining expected results tricky. You might need multiple test runs to check for statistical consistency rather than exact matches.
Right, you can't just assert output equals X. What else?
Self-learning, which we touched on. Systems that change their own behavior over time are a moving target for testing. Designing test cases is hard, and the act of testing itself might inadvertently train the system in undesirable ways.
That's a mind bender. Testing changes the thing you're testing.
It can, especially with online learning systems, and then there's the cluster of issues around transparency, interpretability, and explainability.
Okay, break those down quickly. They sound related.
They are. Transparency is about being able to see the algorithm, the data, the parameters. Interpretability is understanding how the model works in general terms. But explainability is the real kicker. Can you explain why the model made a specific decision or prediction for a specific input?
And with complex AI, the answer is often no.
Often, it's very difficult. The model learned complex patterns from data, but those patterns don't always map neatly to human understandable rules. We might know what it decided, but not precisely why.
Is there anything that helps with explainability? You mentioned LIME earlier.
Yes, techniques like LIME, local interpretable model-agnostic explanations, try to help. They work by perturbing the input slightly and seeing how the output changes to build a local, simpler model that approximates the complex model's behavior just around that specific prediction. It gives clues about which features were important for that decision.
So not a perfect explanation, but better than nothing.
It's a step towards understanding, yeah.
Yeah.
Useful for debugging and building trust.
And this all feeds into a classic QA problem made worse by AI, the test oracle problem. Remind us what that is and why AI makes it harder.
The test oracle problem is the fundamental difficulty of knowing the correct expected outcome for a given test input. How do you know if the test passed or failed?
Right.
With conventional software, it's often clear clicking Save should save the file. But with complex AI, especially probabilistic or self-learning systems, what is the correct output? If it's predicting stock prices, there's no single right answer. If it's generating creative text, what's correct?
Or if the acceptance criteria is vague, like it should improve over time.
Exactly. Or if you haven't purposely defined the operating environment, it becomes incredibly hard to define pass-fail criteria, which is the core job of a test oracle.
Okay, so if we often don't know the right answer, how do we test these things effectively? This brings us to some advanced testing techniques. Let's start with the scary ones. Adversarial attacks and data poisoning. How do we test against those?
Yeah, these are serious threats. Adversarial attacks use specially crafted inputs, adversarial examples that look normal to humans but cause the AI to make big mistakes. Think tiny changes to an image that make an AI misclassify it completely.
And testers need to find these vulnerabilities.
Yes, adversarial testing tries to proactively find these weaknesses. You generate potential adversarial examples and see if they fool the system. If they do, you can sometimes add them to the training data to make the model more robust. And worryingly, these attacks often have transferability. An attack that works on one model often works on similar ones too.
Wow. Okay, and data poisoning. How do we test for malicious data being slipped into the training set?
Data poisoning aims to corrupt the model during training. Testing involves vigilance during data acquisition, strong policies, checks, using exploratory data analysis, EDA, to look for strange outliers or patterns in the training data can help. Sometimes techniques like A/B testing, comparing models trained on different data subsets, or robust regression testing after data updates can catch issues.
Sounds like constant diligence is needed. Now, for the Oracle problem, how do we test when we don't know the expected output? You mentioned metamorphic testing earlier. How does that work?
Metamorphic testing, or MT, is really clever for this. It doesn't need the exact expected output for a single test case. Instead, it focuses on the relationships between the inputs and outputs of multiple test cases.
Relationships. Can you give that average example again?
Sure. Test case 1, input 1, 2, 3, output average is 2. Now we define a metamorphic relation, MR, like permuting the input numbers doesn't change the average. So we create test case 2, input 3, 1, 2. We don't need to know the absolute expected average beforehand. The MR tells us the output should be the same as for test case 1. If it's not 2, we found a bug.
Ah, so you check the consistency based on known properties or transformations.
Exactly. Another MR could be multiplying all inputs by 2 should multiply the average by 2. So input 2, 4, 6 should give an average of 4. You verify these relationships. It's powerful for AI, like image recognition. Rotating an image shouldn't change the object identified. Search engines, route planning, anywhere expected results are fuzzy, but relationships are predictable.
That makes a lot of sense. A really useful technique. What about AD testing? How does that fit into AI testing?
A/B testing is great for comparing versions. You run 2 variants of the AI system, maybe the current one, A, and a new candidate, B, in parallel on real or simulated traffic. Then you compare their performance based on key metrics.
Like which version gives better recommendations or faster routes?
Precisely. You define acceptance criteria. Maybe version B needs to be 5% better on some metric and see if it meets them. It acts as a sort of comparative oracle.
Useful for validating improvements. And what about good old exploratory testing? Does that still have a place with AI?
Absolutely, maybe even more so. Because specs can be vague, and the oracle problem is common, exploratory testing, where the tester simultaneously learns, designs, and executes tests, is invaluable.
How do you structure that for AI?
You can use tours, like a data tour where you specifically explore the training data, its sources, its variety, or a features tour exploring how different input features affect the output. It often overlaps with exploratory data analysis, EEA, interactively digging into data to form hypotheses. And for guidance, Google's ML test checklist is a great resource, covering data, model development, infrastructure. Really practical stuff.
Sounds like a must-have. Any other quick mentions of useful techniques?
Briefly, things like pairwise testing can be useful when you have many parameters influencing the AI to test combinations efficiently. And back-to-back testing, comparing the AI's output against another system, maybe an older version, or even a human expert, can provide a useful reference point.
Okay, great overview of testing techniques. Now let's flip the script. Can AI actually help us testers? Can AI be used for testing?
Oh, definitely. This is a rapidly growing area. AI can assist QA in many ways. We can categorize it a bit. There's using fuzzy logic or probabilistic methods, maybe for predicting system failures. There's classification and prediction.
How would that work?
Think AI for analyzing reported defects. Using natural language processing, NLP, to automatically categorize bug reports, or using clustering algorithms like nearest neighbors to find duplicate defects. That can save a lot of time in triage.
I can see that being useful. What else?
AI for test case generation, optimizing which test cases to create or select. AI for optimization of regression test suites, helping decide which tests to run after a change, making regression much more efficient.
Making regression less painful. Sign me up.
Right. Also, AI for defect prediction, using historical data to predict which modules are likely to have bugs or which reported crashes are most critical to fix first. And a big one is AI for testing user interfaces, assisting with visual regression testing, spotting UI changes automatically, or even helping with GUI test automation, making it more robust to changes. AI is becoming a powerful assistant for the QA team.
That's really exciting. Okay, one last area. Test environments. AI testing seems like it might need special setups. What about virtual test environments?
Yes, virtual environments are often essential for effective AI testing. They offer huge benefits. First, controllability. You can precisely recreate specific, maybe rare or dangerous conditions.
Like extreme weather for a self-driving car AI.
Exactly. Or complex financial market scenarios for a trading AI, things that are hard or impossible to set up in the real world reliably. Second, observability. In a virtual world, you can monitor and record everything digitally, giving you much deeper insight into what the AI is doing and why.
Better than trying to stick sensors everywhere in the real world.
For sure. And third, availability. You can simulate hardware that's expensive or maybe not even built yet. You can test components earlier in the cycle.
How do these help with those specific AI challenges we talked about?
They directly address things like self-learning. You can simulate environmental changes. Autonomy, you can push the system to its limits safely. Big data, you can generate massive, high-velocity data streams. Tools like NVIDIA's Drive Constellation for autonomous vehicles or MATLAB and Simulink are examples of powerful simulation platforms.
Very powerful. And finally, circling back to basics documentation, it's always important in QA, but how crucial is it for AI components? What needs to be documented?
It's absolutely critical, especially given the black box nature and complexity we discussed. Good documentation is vital for transparency and testability.
What should it cover?
Key things include assumptions made during design, known limitations or biases, any ethical considerations, the features used by the model, details about the dataset's collection, privacy, characteristic specifics about the test dataset and methodology, and performance metrics. Clear documentation helps testers understand what they're dealing with and design effective tests.
Excellent. What a journey through the world of AI testing. We've really unpacked a lot from that ISTQB syllabus.
We have. Hopefully everyone listening feels they have a much clearer picture now of the unique challenges, data quality, bias, explainability, the Oracle problem, and also the specialized techniques QA pros need.
It's definitely not just business as usual testing. It's about grasping machine learning concepts, managing data rigorously, dealing with autonomy and evolution, using new tools and techniques like metamorphic testing.
And appreciating that highly iterative development cycle.
Exactly. And for everyone tuning in on InsideQA, whether you're prepping for that ISTQB AI tester exam or just leveling up your QA skills for this new AI era, mastering these concepts is, well, it's becoming non-negotiable, isn't it?
It really is. It's about ensuring these powerful systems are built responsibly, robustly, fairly effectively. It's moving beyond just testing code to assuring the quality of intelligence itself.
So here's a final thought to leave you with. As AI keeps getting smarter, keeps pushing boundaries, how does our role as human testers change? Will we become more like AI curators, focusing on the training data, the ethics, interpreting the why, rather than just verifying the what?
And what new kinds of testing, maybe more human-in-the-loop strategies, will we need for systems that constantly learn and improve on their own?
The future of QA in an AI world isn't just about testing the machines. It's about defining what quality even means when intelligence is involved. What stands out most to you from today's deep dive, and what aspect of AI testing will you explore next?